In this section, I'm going to be talking about stress at a point in soil. And that's an important topic because, for example, if we have a slope, we want to know what is the stress in that slope so we can figure out if the slope's going to fail. Same thing for a footing. If we load the soil vertically, we want to know what is the stress at some point beneath the soil. Okay, the state of stress in the soil is fully defined by the Cauchy stress tensor. I want you to always think of stress as being a tensor-valued quantity. There are 9 components to the Cauchy stress tensor: sigma xx, xy, xz, yx, yy, yz, zx, zy, and zz. And I'll draw those here in just a second. I'd also point out that the stress tensor is symmetric. So even though there are 9 different values within the 3x3 tensor, sigma xy is equal to sigma yx, sigma xz is equal to sigma zx, and sigma yz is equal to sigma zy. So there are actually only 6 unique values there. All right, now the different stress components are illustrated in this figure that I copied from Wikipedia. They're using 1, 2, and 3 for their directions rather than x, y, and z. That's just something we need to be aware of. In mechanics, it's common to use 1, 2, and 3. It's also common to use x, y, and z. Don't get confused by them. You know, this is just a notation issue that we have to be aware of as we move forward. Okay, a couple things to note before we move forward is first, we often ignore some of the components of stress when we analyze stress in geotechnical engineering. We don't do this because it's okay to do it. It's just because it makes it easier. And so it's simpler to ignore some stress components, so we do it. A good example is the Mohr circle, right? You've all been pretty familiar with Mohr circles for a long time. We have an element that's two-dimensional. It has a vertical stress, a shear stress, and a horizontal stress. Then we sketch a Mohr circle just based on those components, right? We have a tau and a sigma axis, and we can plot the points, the vertical stress and shear stress, horizontal stress and shear stress, and then draw a circle. I'm not very good at drawing circles with this tablet, but anyway, there's my Mohr egg. Okay, the problem is, what about the out-of-plane stresses? We're only dealing with 3 stress components here of the full Cauchy stress tensor. So although this is easy, it's not mechanically rigorous, and we should be aware of that. All right, another issue that we have to deal with is that we often know stresses on certain planes, typically vertical and horizontal, but we want to know what the stresses are that are acting on some rotated planes. Good example is this slope stability problem here. So if we want to understand what is the shear stress on the failure plane at failure for a slope, we're going to want to rotate the stress condition from vertical horizontal over to some coordinate system that's relative to the slip surface. We want to know what is the normal stress acting on that slip surface, and that allows us to estimate the shear strength of the soil. So there are a lot of times when we want to rotate stress conditions and solve for principal stresses and things like that too. And slope stability is just one example. Let's move on now to talking about stress rotation. We'll start by doing this in 3 dimensions. And the way that we represent this is using a rotation tensor, which we'll call A. So sigma prime with 2 lines under it to indicate it's a rank 2 tensor is equal to A times sigma times A transpose, where A is the rotation tensor. Now I'm using the prime here to indicate stresses on a rotated coordinate system, not effective stresses. That might be a little confusing, and I apologize for that. It's just that the prime is a common notation to indicate rotated stresses. Let's look at 2 dimensions, which is actually more commonly used in geotechnical engineering because we're often working with Mohr circles. So let's say that we start with an element where we know the stresses on horizontal and vertical planes. That's a common condition where we think we know those stress components and can draw a block diagram representing vertical and horizontal stresses and shear stresses. But let's say that we're solving a slope stability problem and we want to know what the stresses are for that soil element on some rotated planes, say normal and perpendicular to some trial failure surface. So here we would have a new coordinate system, sigma xx prime, sigma yy prime, and then sigma xy prime in accordance with some x prime, y prime coordinate system. And let's say that the xy prime, the x prime, y prime coordinate system is rotated by some angle theta relative to the original coordinate system. Well, now we can write out the rotation tensor terms here in matrix form. So sigma xx prime, sigma xy prime, sigma yx prime, and sigma yy prime is equal to that rotation tensor, which in this case is just a combination of trigonometric functions. So you have cosine theta minus sine theta. The bottom left is sine theta. Sorry, my tablet messed up there, but that's a sine theta, and then cosine theta in the bottom right. That multiplies the original stress tensor, which is acting on horizontal and vertical planes. And then, of course, we have to have the transpose of that rotation tensor. The rotation tensor concept, by the way, is the same in 2 and 3 dimensions. It's just that in 2D, you only have 2 components of the rotation tensor, whereas in 3D, you end up with 3 components. So the transpose now just involves a minus sign on the sine term on the bottom left and a plus sign on the top right. Now, if you were to expand this out, you could do a matrix multiplication there on the right side, and then write out the direct expressions for sigma xx prime and sigma yy prime and tau xy prime. You would end up getting these expressions here, which can be really convenient if you want to just write a code where a user could input some rotation angle theta and you want to automatically calculate stress components on that angle. We'll also talk later about a graphical method for determining stress components on rotated planes using the Mohr circle combined with a concept called the pole. But for now, we're doing it algebraically, and again, these expressions can be quite useful for a program. You could easily program this up in Excel or MATLAB or any program like that. Now you'll notice the expression involves only the stress components in the original horizontal and vertical coordinate system. So sigma xx, sigma xy, sigma yy, or tau xy, and then the rotation angle theta. So as long as we know theta, we have everything that we need here to compute the stresses on a rotated coordinate plane. Another thing we can do using the stress rotation principle is develop algebraic expressions to solve for the principal stresses. We know we can get the principal stresses by drawing a carefully crafted Mohr circle, which I'm struggling with here with this drawing tablet. But anyway, then you find the maximum and minimum stress values. So sigma 1 is at the far right side, sigma 3 is at the far left side. What we know is that the principal stresses occur where the shear stress is 0. So the initial stress condition here involves vertical, horizontal, and shear stress, but we can rotate the stress condition until the shear stress is equal to 0. So all we need to do is use our previous expressions, set tau xy prime equal to 0, and then solve for theta. So instead of knowing an angle, now we know that tau xy prime is equal to 0, and we can solve for that angle. You end up with this expression here, tangent of 2 theta is equal to minus 2 tau xy over sigma xx over sigma yy. Okay, and then you can plug in that value of theta after solving this equation to get your sigma 1 and sigma 3 values. Sigma 1 would just be sigma yy prime, sigma 3 would be sigma xx prime, or potentially the other way around. Sigma 1 is always bigger than sigma 3, just something to remember. So let's say we have an example where sigma xx is 100, could be 100 kPa, no units, we'll just stick with numbers here. Sigma yy is equal to 50, and tau xy is equal to 25. Well, if we solve for theta that's associated with the principal stresses by using the expression tangent 2 theta was minus 2 tau xy over sigma xx minus sigma yy, you end up with theta being minus 22.5 degrees. Sigma 1 is 110.36, and then sigma 3 is 39.65. another thing we can now look at is principal stresses fundamentally as being an eigenvalue problem. So we've talked about how to derive principal stresses by drawing a Mohr circle. You just find the maximum and minimum stress points that lie right along the x-axis. We've talked about how to derive them algebraically using a rotation approach in 2 dimensions. We haven't talked about it for 3 dimensions, and it's actually really useful to do this as an eigenvalue problem now when we go to 3D, although it also applies equally well to 2D, and I'll illustrate that using an example here in just a second. So let's say that we have a Cauchy stress tensor with the xx, xy, xz, and so forth components. And now I'm going to sketch the coordinate system. So we'll say x, y, and z is just the traditional orthogonal coordinate system. I'm also going to sketch here the rotated coordinate system, x prime, y prime, and z prime. And these are the coordinate directions that happen to correspond to the principal stresses. So that's similar to what we did before, right? We rotated until we found the theta that gave us the principal stresses. We're doing that same thing now, it's just in 3 dimensions. All right, so our task now is to find exactly how we have to rotate the XYZ coordinate system. And it's going to be 3-dimensional rotation now, not just a single rotation in 2 dimensions. But we want to find the rotated axes E such that the stress tensor times a particular stress component E sub I, is equal to lambda sub I times E sub I. Now let me explain what these things are. E sub I is a unit vector, and it describes the coordinate direction for one of the principal stress directions. So E sub I would be aligned along x prime, y prime, or z prime. And there are 3 of these unit vectors, and they correspond to the subscript I means the ith principal stress. And then lambda I is just the value of the ith principal stress component. And there would be 3 of those as well. Well, it turns out that it's really easy to solve for lambda. You just compute the eigenvalues of the Cauchy stress tensor. There are a lot of programs that allow you to calculate eigenvalues. You can easily do this in programs like MATLAB or Python with the appropriate library. I'm going to do it using MathCAD here in just a second. And the E values are the eigenvectors of sigma. So you can compute those pretty easily too and solve this whole problem without doing algebra. Okay, this is a MathCAD sheet where I'm illustrating this point. So I've developed the stress tensor, same one we did before with 125 and 50 in there. You can see we get the same principal stresses, and now we get those eigenvectors as well. Let me just show you that this is also easy for a 3-dimensional stress tensor. Let's keep the upper left 4 values the same as that 2-dimensional stress tensor, but now we'll add some stresses in the out-of-plane direction. Right, so it's easy to calculate the eigenvalues for that. The principal stress has gone up a little bit, the major principal stress. The minor principal stress is now smaller, and you can also easily compute those eigenvectors this way as well.